Get started today. So we're continuing our discussion of recursion today, and we're going to be going over the Towers of Hanoi problem and the Sudoku problem that you see in the notes, and that will get you ready for the lab that you'll be starting tomorrow called Shapeshifter, which is essentially a puzzle solving lab that's somewhat similar to Sudoku puzzle. So one thing we're going to see is that recursion is particularly good for solving puzzles because both of the recursion problems we're considering today are puzzles. Before I went into that, I did want to show you a couple other examples of recursion because it's not always natural when you're first starting out with recursion to think about things recursively. But there are some very beautiful recursive structures out there, some natural, some that are, quote, artificial. One artificial kind of structure called Mandelbrot images was developed by a mathematician named Mandelbrot, and they have recursive definitions to them that you start out with some kind of structure and then you recursively embed smaller examples of the same structure. So you can kind of see that here, that what you have is a rather large structure that kind of has a yellowish outline, then kind of a pinkish interior going to red, then green, then blue, then red with a white spot. And what's happening is that increasingly smaller images of the outer image are being embedded in the outer image. So you're just getting smaller and smaller images of the original, and that's what's giving it this kind of spiral appearance. And then the same thing with these little doohickeys out there. Again, they're just smaller images that are the same images, just slightly scaled down. So it's like starting with one image, now printing it at the same point but at 99% scale, and then at 98% scale, and then at 97% scale. And it creates these really kind of cool and unusual images. And these are all essentially just recursive images. Okay, snowflakes. The way things crystallize is often somewhat recursive in that you get crystalline structures that essentially create just smaller images of themselves and embed themselves. So those are examples of recursion. Another example of recursion that you've been dealing with all semester is file directories. Okay, so if you think about your top level user directory, so on my computer it's user BVZ, well, or not, users. Okay. In fact, we can start with the top level directory, which is just the so-called root directory, and you can see that's what the root directory is. And then each subdirectory is in effect a recursive directory. Okay? And you can keep going, so we can go to now users. That's the next level of recursion, which has three subdirectories called shared BVZ and IT staff. And then recursively, we can go down into, so we can CD down to users now. Whoops, CD down to users. And now look at BVZ. Okay, so we're kind of doing another recursive descent through my directory structure. Now I could descend into CS140. Whoops, first I have to CD to BVZ. And if I look, now I can descend into CS140. So this is kind of recursively diving down through my directory structure. And eventually, what stops my recursion? At what point would I no longer be able to say CD? You don't have any more directories. I get to a file. So for example, let's see, exams.html is not a directory, it's a file. So if I try to say CD, it says not a directory. So that's the so-called base case. Files are the so-called base case. I can't descend recursively into a file. So that's the base case. So remember, recursion has two cases. So it has the base case, okay, which stops the recursion and which gives you an actual solution. So actually gives a concrete solution to an instance of the problem. So for example, when we did the factorial, we know that 0 factorial is 1, and we know that 1 factorial is 1. So those are the two base cases for factorial. And then we have the recursive case, where we define a problem in terms of one or more subproblems and combine the results of the subproblem. Okay, and an example of that was n factorial equals n times n minus 1 factorial. So we're expressing it in terms of n minus 1 factorial, then combining that by multiplying it by n. So that's the essential characteristic of recursion. And I know I haven't made many references to the textbook this semester, but I feel as though this is one case where the textbook has an excellent section of about 13 pages on recursion. And if you're looking for yet another alternative source of information on recursion, I strongly recommend that you look at the textbook and its section on recursion. It gives you a few other problems that deal with recursion that we won't go over in the class, but of course I'd be happy to answer it during office hours. One is drawing the tick marks on a ruler, and I think it was a particularly nice example of recursion. And the book actually did talk about three kinds of recursion: linear recursion, binary recursion, I believe it's the third one was multiple recursion. So with linear recursion, you have a single recursive call. And factorial is an example of that because it's n times n minus 1 factorial. So you have a single recursive call. Binary recursion, as you might imagine, has two recursive calls. So you break the problem into two subproblems. So it has two recursive calls. So I'll say break recursion into two subproblems. Break problem, not recursion, break the problem into two subproblems. So an example of that would be the Fibonacci number, that f of n equals f of n minus 1 plus f of n minus 2. That's a binary recursion problem. Now, last time we went over binary search, and you'll remember that binary search had an if then else. So it was basically if target in lower half, then we called bin search with the target in the lower half of the array, and else we called binary search with the target in the upper half. So just a show of hands, we're going to vote on whether this represents linear or binary recursion. So how many of you think that this represents linear recursion? Okay. And how many think it represents binary recursion? Okay. Most of you think binary recursion. Okay. That's why I'm going over it, because it's actually linear recursion. And the reason it's linear recursion is we're not actually dividing the problem into two. We're choosing one or the other subproblem based on whether the target's in the lower half or the upper half. So this is, in fact, a single recursive call. It's just that the recursive call is determined by the if-else statement. The binary recursion is literally you have two recursive calls that you make. Here, yes, you see two recursive calls, but only one of them gets made. So, in fact, we're only when we break the subproblem down, we're actually breaking it down with a single call. It's just we have to figure out whether the call is going to be to the lower half or the upper half. So don't get kind of sucked into just counting blindly the number of calls. That's not what determines linear or binary recursion. What determines it is the number of calls actually made. And in this case, you only make one of the two calls. So it's linear recursion. You're actually only defining it in terms of ultimately one of those two. Okay? Questions about that?
So
yes, Joe?
If it's binary, it actually makes two separate
Exactly.
calls.
It makes two separate calls. Yes. So good. So has two makes. Okay, so we'll say makes two separate recursive calls, and it makes them. It doesn't just have them listed. So that, yes?
So does that mean, like, say it made like 10 calls, and then, so when it's on its way back out, it would call itself like 10 more times? Is that?
I think what you're talking about is multiple recursion. Let me define multiple recursion, see if this answers your question. Okay, so multiple recursion happens when you may call yourself when the same instance of a problem solves three or more subproblems. And that's what we're going to go into today. This is often where we get into so-called puzzle solving and what's called backtracking. Okay, so I'll kind of give you a quick preview without, at this point, going into great detail. So today was Sudoku. Well, actually, if you haven't read Sudoku, you won't actually kind of know what well, we'll still do it. So Sudoku, actually, let me just show it to you quickly. So for those of you not familiar with Sudoku, which you should be because you should have read the notes before you came to class, but in any case, you start with a puzzle that has 9 panels, 3 across and 3 down. Each panel consists of 9 cells. And your goal is to fill the cells in such a way that within each panel there are filled with the numbers 1 to 9 and no number is duplicated. In every row, each number between 1 and 9 appears only once. And in each column, each number between 1 and 9 occurs only once. So for example, here's an example, given this as the initial problem. So the initial problem always has a few entries filled in for you. And then here's an example solution. So you see 8, 6, 2. Those are the original ones. But if you look at this panel, you'll see that no number is repeated twice in that panel. You'll see, if you look at the first row, that no number is repeated twice in that first row. And first column. And now if you look at the first row, nothing is repeated twice in the first row. And in fact, if you look at any other row, you will see the same holds for it, that no number is repeated. If you look at any other column, you'll see that no number is repeated. And if you look at any of the other 8 panels, you'll see that no number is repeated. So that's a solution to the puzzle. Okay? And the way that you can solve, one way that you could solve this puzzle, not an interesting way to a human, that's not the way we do it by brute force, but you can do a brute force search of the so-called solution space by starting with the very first element, which is the upper left-hand corner, and choosing in turn each number between 1 and 9. Okay, so we can start with the number 1, and we can then check, first of all, based on what I've just said, what's the first thing I need to check before I proceed? Need to check the row to make sure that there's not already a 1 in that row. What else do I need to check? The column. I need to make sure there's no 1 in that first column. Someone other than Doug, tell me what's the third thing I need to check?
The box.
The box. Okay, so this panel right here, made to make sure there's no 1 yet in it. And there's not, so all 3 conditions are verified, so this is a possible solution. In fact, you can see over here that 1 ultimately will lead to an acceptable solution. So having checked that, we can now recursively solve this puzzle by saying we're going to solve the puzzle by filling in the remaining entries. So we assume that we are always starting from the upper left-hand corner, moving left to right until we've filled the first row. Then we'll move down and we'll fill the second row. Then we'll move down and fill the third row. And we'll keep doing that till we solve the puzzle. So in this case, after filling in 1, we recursively call it. And we're going to see whether we can... So we've got 1 here. Now, the next number we come here. The next number we're going to try is 1. You say, wait, No, impossible. We already used one. But remember, this is a computer. We have to give it a algorithm, and it doesn't really know when we've entered it what numbers we've already used, so it's going to basically write a loop that just goes from 1 to 9. And it's just going to dumbly plug in each number. So it's going to start by plugging in 1, and of course we see immediately that that's not a good number. It violates a couple of our conditions, right? Which conditions get violated?
There's a 1 in that row, there's a 1 in that box.
Very good, Gerald. So there's a 1 in the row, there's a 1 in that box already. So now we have to go and consider 2. Okay? And 2 is just as bad for actually 2 is bad for all 3 reasons, right? Same row, same column, same panel. So we try 3. Is 3 any good? Why not? Same row. So we try 4. 4 any good? Same column. So we try 5. Does 5 look like it's got a possibility? Yep. In fact, if you look over here, you'll see 5 again is in the solution. But at any rate, we now would try putting 5 in here, and we would recursively call it, and now start filling in those. Now, the issue, thus far you can see that each number I fill in is a winner. Okay? So every number that I am putting there is going to be a winner. So 1, 5, if I come over to this one, the first number that's going to satisfy all the conditions is going to be 4. If you quickly look at it, 1, 2, and 3 are no good. Okay, so we get to here, and what's the first number I can try here that's going to satisfy all 3 conditions? It is not 2. I heard someone say 2, but 6. 6 is the first number that's going to satisfy all the conditions, right? There's no 6 in the row, 6 in the column, or 6 in the panel. But looking at the example solution, did 6 work? No. So eventually, we're going to, if we keep trying to solve the problem, we're going to find that 6 leads to some kind of contradiction. Okay? It's not going to work out. So, for example, we could go over to here next, and we could try 7, which seems to work fine, right? Do we agree that 7 works fine there? It's the first number. Actually, that's not even the... Actually, 4 would be the first number we would try here, correct? No, 4, 5, 6, 7 would be the first number, right? Okay, so what's the number that has to go here? Based on 8 would have to go there, but it can't, right? Do we agree? So what would happen is eventually we'd get to here, we would cycle through all of our numbers 1 through 9 and find out that no number works. So we would have to do what's called backtracking and throw out that number and move back to this one right here, which is 7, and say, okay, 7 didn't work. So the next number we could try would be 8, correct? And then 7 would seem to work over here. So we would move down to the next row, and all we know is based on the solution that somewhere along the line in one of the following cases we're still going to come to a contradiction. So the bottom line is that we may come back multiple times to the same location and have to try again. Okay? And we could make potentially up to 9 recursive calls. Okay? That's unlikely because you see that in this, when we got to this particular cell, there was only two possibilities, 7 and 8. But it's possible that you could make up to 9 recursive calls, right? Because there's 9 possible numbers, and in very hard puzzles where they hardly give you any information at all to start with, it's quite possible that you might come to a square or a cell where all 9 numbers meet the 3 conditions. So you might have to do a recursive call with all 9 elements. Well, that, getting back to here, getting back to there, would be an example of multiple recursion, because you can call the same instance of a problem up to 9 times. Okay? So and you might still be a little confused because you're thinking, but it looks like you're just calling Sudoku each time. But in effect, each time you're calling it with a different number. First you might be calling it with 1, then you're calling it perhaps with 2, then you're maybe calling it with 3. So each recursive call is a different number, different subproblem. Okay? So what we're actually looking at today is multiple recursion. And last time we showed you examples of linear and binary recursion. So questions? So I'm going to continue actually with the Sudoku example because we have gotten, that's the one that we've gotten into. So we've already talked about the essential conditions. So the conditions are no duplicated number in a row, no duplicated number in a column, no duplicated number in a panel. So if we're thinking about a solution, okay, in general, so let's say we're trying to solve Sudoku. Okay, and I'm going to use pseudocode first. Okay, so we're not going to worry just yet about the data structures. I'm just going to call it my grid. So I have this is a 9 by 9 grid. Okay, maybe it's a 9 by 9 array, maybe it's a vector of vectors, maybe it's what Dr. Planck used, which was a vector of strings. Okay, you could use a variety of data structures to solve it. And then we want to know at which row and which column we want to start our solution. So initially the call will be to Sudoku with row 0, column 0, because we need to start at the very beginning. Okay? So what we're going to do is we're just going to run through the numbers 1 to 9. Again, this is pseudocode for number 1 to 9. Okay, so, or number equal 1 to 9. So I'm just going to start running through. Again, I don't know whether or not there's a solution. Actually, before I do this, let's go back. Before I say number equal 1 to 9, what's the first thing I should check based on what I see there? Is there a number already there? Okay, I'm not allowed to change the numbers that the puzzle maker gave me. So for example, when I reach this particular cell right here, I'm not allowed to change the 3 to any other number. The numbers the puzzle maker gives me in the original grid are immutable. They cannot be changed. So in fact, the first thing I really need to do is check to see whether I already have a number there. And in this case, you can see we're using dashes to represent numbers not already there. This is a good exercise to think about. If I'm using dashes, what does that mean about the representation of those numbers. Could I actually be using integers or not if I'm using dashes? I see both Senia and Gerald shaking their heads. What? It's a string or a character that I'm representing. So let's say I wanted to use a number, okay, because naturally these are numbers. What should I replace the dash with? What's a good number to replace a dash with? -1, for example. Any number that's not 1 through 9, right? But choosing an arbitrary number like 563 isn't really, you know, something that makes a lot of sense. Okay? -1's a good one because a negative number really kind of steps out there and says, hey, shakes you, and it's like, wow, a negative number can't be it. Okay, 0 would work too, right? It's not 1 to 9, but 0 doesn't quite have the shock value that a negative number has. So -1, I think, is the best choice here. But at any rate, we're using dashes. So the first thing to actually check is if the grid row column is not equal to a dash, then we should say for number equals 1 to 9, we will first check to make sure that it's valid to fill in that particular row with that number. So we might say is, let's see, we might say if is row valid, say row and number, need another, there's 2 right parentheses there, and is column valid, row number. Now we might have to pass the grid too, but I don't have enough space, and is panel valid. And now I have to probably give it both, say, a row, column, and a number. This should have been column, by the way. So somehow I'm going to have to do a calculation to figure out what panel I'm in. We'll get to that. Okay? And then, if all those conditions are valid, then we can try to solve Sudoku. With the same grid. And now I'm just for the moment going to say row plus 1 because we'll always do these things, whoops, not row plus 1, row, column plus 1. Okay, I know this isn't perfect. So if it's true, we return true because we succeeded. Okay, and else we simply go on to the next number. So if any of the 3 conditions fails, we go on to the next number. If Sudoku fails with that number, so actually before we go on, we would probably tentatively have to set grid row column to be equal to number, because somewhere we have to actually fill it in, right? So then we ask, is it valid? If it is, let's try to solve for it. And if not, then we're going to try another number. And if we get out of the for loop, then we return false because none of them worked. We can only get out of the for loop if none of the 9 numbers worked, right? Does that make sense? Disagreements? If at any time one of the 9 numbers worked, we return true. So the only way we get out of the for loop is that none of the 9 numbers worked. So we return false in that case. Okay? Well, we also have to consider the case that the already had a number. So that was if the grid did not contain a number. If it does, we're just going to return the result, and again, this is not yet perfect, of looking at Sudoku with the same grid, row, column plus 1. Right? Does that seem reasonable? Does this seem like kind of a reasonable outline of what a solution might look like? I see a lot of kind of puzzled looks, so can someone articulate a question that might be bothering them? Now, this isn't quite right, so we're going to talk about what's not quite right, but I'm just asking if this is kind of seemingly a bare bones outline of a possible solution. Okay, so basically we're just filling in the next unknown cell with a number from 1 to 9, and if it satisfies the 3 conditions, then we're tentatively saying, okay, that number will go in that cell, and then we'll solve the rest of the puzzle. For those of you who are crossword puzzle solvers, how many of you like solving crossword puzzles? 1. Seriously? 2? Okay. How many of you have attempted crossword puzzles? Okay, most of you. Okay, so when you attempt a crossword puzzle, it is a recursive exercise, right? You kind of come up with, you solve one of the clues, right? You say, oh, I know the answer to this clue, and you write the answer in, right? And then you solve the rest of the puzzle. So that's a recursive solution to the puzzle. You're actually doing it recursively. You're now just solving a subproblem where one of the entries has been filled in. And for those of you who do crossword puzzles a lot, you know that sometimes what you put in is a guess, right? Sometimes it's wrong. And you have to later go back and erase it. We call that backtracking. Okay? That's all we're doing here, is we're putting in a guess. Now, not as sophisticated. You make a very educated guess. We're not making such an educated guess here. We're just saying anything that is legal, we will try. But we fill it in, and then we move on, and we say, okay, given that we filled in that square, let's see if we can fill in the rest of the puzzle. And that's what this code is doing. Okay? So it's just a recursive solution. Now, I'm saying that there is one issue with this. Eventually, this code's going to core dump. Okay, why is this code going to core dump eventually? And it's not because I didn't get the recursion to, the recursion will stop, okay? If the number is, actually, yes. The recursion within here will stop if I exhaust the numbers 1 to 9. And here, if this one returns, I will return. But there's an issue. What issue did I kind of overlook? The column plus 1. What happens when I get to the end of the column? It just keeps going. Okay? Which isn't very good. Okay? We're all familiar with what happens when you step beyond the bounds of an array. for those of you lucky enough not to have segfaulted it yet because of that, what typically happens is we segfault. So we actually have to check and make sure that the column is valid when we add 1 to it. And if it's not, then we need to add 1 to the row, right? And eventually, in the happy case, where we get both past the last row, we've in essence solved the problem. Okay? That's what will eventually solve the whole thing, is if the row that we get is greater than 9. Well, in this case, it's actually equal to 9 because we started our rows at 0. So if the row is equal to 9, it means we succeeded. Okay, so actually, we would have to do a little bit of modification here. So if row is equal to 9, then I'm going to return true. Because there's nothing more to consider. I've gotten every number I put in was valid. Okay? I couldn't have kept calling Sudoku with any invalid numbers. So if I get to row 9, I'm in great shape. I've actually solved it. There's no more numbers to fill in. Okay? So a very simple, so else, what's another bad possibility based on what happened? Well, column could be equal 9, right? Because I just always added 1 to column. So it's possible, based on the way I wrote this thing, that the column could have equaled 9. Correct? Okay. So there's a very kind of easy right here solution, which is just return Sudoku grid row plus plus. Man, out of room. Let's see if I can make this smaller. So else, if column equals 9, I will return Sudoku of grid row plus plus. Boy, I still am having trouble. 0. So for those of you who can't read that, it says Sudoku grid comma row plus 1 comma 0. Okay, what I'm doing is taking the lazy way out, which is I am resetting the row by adding 1 to it, and technically I need to, before I progress, I need to actually, and I'm going to add an else here, but technically before I progress, I need to again check to see if the row is equal to 9. Rather than do another check to see if row is equal to 9, I just call Sudoku recursively, having fixed up my row and my column. Okay, it's not a big hit. Yes, Doug?
So what's the difference between returning, like doing a return callback to the function and just doing a callback to the function?
So when I say return, I'm saying return whatever value the function returns.
So that doesn't keep going recursively.
Yes, it does.
It does.
But so what's happening is this is going to be a bool. So it's going to return a bool, true or false. Either I succeeded or I failed.
So what returns, it says...
So it's saying return whatever value this recursive call gave me. So if that recursive call gave me true, I'll return true. Let me do something that may seem a little easier. Let's say I had factorial.
So if you just call the normal, if you just call a normal call back up to the function, it saves the current state and then...
Yes, so let's go over that again. So let's do it simpler. Okay, let's do factorial. Okay, so if n equals 0 or n equals 1, okay, we return 1. Else we return n times factorial n minus 1. So it's the same situation that we have right here, right? We're returning the result of our recursive call. Okay, I'm just simplifying with a simpler recursive function here to answer your question. Okay, so remember from last time what happens, let's say we are in main. Okay, and let's say we say we have int x, and let's say we say cout, enter factorial to compute. And then we say cin x, and then we say cout factorial x. Okay, so that's our main. And let's say the user enters 3. Okay, so what happens is we start, remember there's a stack, so main, and it has a value for x, which is 3, based on the fact the user input 3. Okay, main calls fact of 3, so n is equal to 3. Okay, so it says, is n equal to 0 or 1? No. So this one is going to return n, which is 3, times fact of 2. Right? So it's calling fact of 2. So this is fact of 2. It has the value of n equals 2. So we're pushing what are called stack frames. Okay, so each call to fact has its own stack frame and its own set of local variables. So the n is never getting overwritten. Okay, so this one is going to be 2 times fact of 1 is what it's going to return, right? So we call fact of 1, and it has n equals 1. Okay, at this point, n is equal to 1, so we return 1. Okay, so we pop the top stack frame, and we return 1. Okay, so 2 times fact 1 is really, it returns 1. So it's really going to return 2 times 1. So it's taking the return value, multiplying it by 2 to get 2. Okay, so it's returning 2. We're now going to pop off this one, and fact 2 returned 2. So now we have 3 times 2. So again, we're taking the return value that fact returned, which is 2, multiplying it by 3, and we return 6 to main. And we pop this one off. Okay, so we're always just that we're allowed to use the return value. So that's what we were doing here. We were taking the return value and multiplying it by n. Here, we're just taking whatever the return value is and passing it back unaltered. If we get back false, we return false. If we get true, we return true.
So
Okay.
what's the difference between that and actually making the call without a return statement?
Without a return statement? So if I make it without the return statement, there's two possibilities. One is that it's a void function. So if I have something that's void, like foo, and I call foo, well, if it's void, I can't use return with it because void doesn't return anything, right? So that'd be one case. Or maybe I'm saving the value. Maybe I'm saying, maybe this is foo is fib. So maybe what I decide to do, if this is n, maybe I decide to say fib 1 equals fib of n minus 1, fib 2 equals fib of n minus 2, return. Now that may not be answering your question, which is, now it's not part of the return statement, but I save the return values. Most of the time when I do recursion, I'm getting some value back that I need to use. Okay, that's kind of the definition. It's implicit in the definition of recursion, which is that I have the same instance of a problem. I define a problem in terms of one or more subproblems and combine the results. So usually something's coming back from the recursion, a solution to the subproblem. Okay, but if it is possible to have a void function here. Maybe I'm doing something to an array. Okay, actually a classic case is sort. Okay, I might be sorting an array. So I might sort an array. And one classic algorithm says divide the array into two halves, putting all numbers less than something into the left half and all numbers greater to it into the second half. So it might be put all numbers less than array of 0 in the lower half. Put all numbers greater than argument, or say greater than equal to array 0 into upper half. So now basically all the numbers less than array of 0 are in the lower half, all greater in the upper half, right? So now we could recursively call sort on lower half, sort upper half. Now we have the situation that you were talking about where I don't have anything returning, but in effect I did, because my sorting is in effect recursively sorting the lower half. My second call is in effect recursively sorting the upper half. When I come back, each of the two halves is sorted, and I know that all the small numbers were in the lower half and all the big numbers were in the upper half. So when I'm done, I kind of know that the array is sorted. So that would be an example where I don't actually return anything out of the function, but one of my parameters is kind of getting modified. I guess the point is recursion is always modifying something. Okay, you always want something from the recursion. Okay, coming back to here. Any other questions about what I did here? Yes?
Should the second if statement, where it says if grid or row column, should that be equals to the hyphen instead of not equal to?
So if it's, no, You're right. Thank you. So this should have been equal to a hyphen. You're right. Because I only want to do it if it's not been filled in. Thank you. If it's not been filled in, then I consider it. Thank you. Other questions? Okay. So what I'm going to do now is go over Dr. Planck's actual code because I think it helps to see what he did. I'm not going to go over it in its entirety. For example, the printing, he has some functions. One, to print the grid to the screen in a nice way. So print screen will print it very nicely with some, here's print screen. It will print the grid very nicely with some spaces between the different cells. And print convert, there's a image making function, Linux command, or available on Windows or Mac called convert, that takes a whole bunch of very gnarly looking parameters. Here's the command. Okay, not even going to try to tell you what this is doing, but, well, actually, sure, it's fun. Create a 234 by 234 pixel. This says create a canvas with a black background. This says that on that black canvas, whatever you draw has a black background, and that whatever you fill onto that white background is black. Then these are the shapes that are being drawn. So this is a 24 by 24 shape with a certain label, and the geometry is 24 by 24 at offset 3 by 3. So x position 3, y position 3. This gravity says to center the label. This gravity is kind of useless. This composite, there are different ways to draw onto images. For example, you can have whatever the source pixels are, replace whatever is on the background. That's what you're used to. You can XOR an image if you're trying to get transparent effects. Sometimes you see the Mac come up with my mail messages and they look somewhat transparent. It's using a different form of compositing for that. So there's a whole bunch of different ways you can combine background and foreground pixels. So that's just telling it the way to do it, which is to lay the pixels down. At any rate, what this command does is it creates a very pretty picture that looks like this. That's actually, instead of screen art, a nice JPEG. Okay? We're not going to worry about it because it's relatively straightforward, and you would have to know, in the case of convert, what the parameters are. What we're really concerned about is solve. And again, Planck is old school. He uses ints rather than bools. One of you made a good Piazza post. You said, why can't our functions return bools? The answer is they certainly could. In fact, my preference is that functions that are returning a true-false result return a bool. But when C was introduced in the 1980s, it didn't have a bool data type. It only had ints. So C used ints. Dr. Planck went through graduate school in the early 80s. So he's used to using ints, and habits die hard. So even when he migrated to C++, Dr. Planck uses ints. And you will have Dr. Planck for 302 next semester. Therefore, we're using ints. If you were going to have me for 302 next semester, I would change all these notes and make them into bools. But it's just a difference in style is all. Neither one is better than the other. So, whoops, but that's not good. What the heck did I do? See, that's doing compositing. If you can barely see what's underneath this message right here. It has some transparency. So it's doing an act that's called compositing, but it's combining the pixels in a way that allows the background to slightly show through and create some transparency. Cool things you can do with imaging. Okay, at any rate, we care about solve. Here's those functions I was talking about. Asking about is a row valid, is a column valid, and is a panel valid. And then the recursive solve is the one that is taking a row and a column. You can see here's our grid, and Dr. Planck is storing the grid as a series of strings. So each row is a string. So the strings will have values like, say, -3, 6, minus or dash 4, dash 2, dash 8, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Is that 9? 3, 6. That really is 9. Yes. So each string has 9 characters representing the values of the cells in that row. So the vector is really a vector of 9 strings. Each string has 9 characters. Okay? So grid is really, grid equals vector of 9 strings. Each string is a row, and each string has 9 characters. Each character representing the value of a cell in that row. Okay? And then he is keeping a vector of ints called checker. And conceptually, what he is doing is conceptually, this isn't quite how he implemented it, but conceptually, it is a array where vector where 0 doesn't matter. But when he's checking a row or a column or a panel, what he's going to do is, if that row already has a 1 in it, he's going to set the value to 1, and if that row doesn't yet have a value in it, let's say that row doesn't yet have a 2, it would be 0. So for example, for this row right here, the vector, conceptually, we don't care about 0, 2, 3, 4, 5, 6, 7, 8, 9. Conceptually, 1 is a 0 because it's not yet part of this row. 2 is part of the row, so it's a 1, meaning it's already in the row. Is 3 a 1 or a 0? According to this. It's a 1 because it's already in there. So this is checker. Is 4 a 1 or a 0? Based on what you see in this string right here. Why? Is it, or is 4 in that row or not? Yes. So we're actually, is the number actually in the row? Yes. Okay, 5, is it actually in the row yet? No. So basically all that, and I'm going to fill them in quickly. 6 is in there, 7 is not, 8 is, 9 is not. So basically it's a way when we ask is a row valid, we can, if we are asking is 7 in this row, we can quickly determine, oh, no, it's not in the row. Okay, but he's going to reuse it. He's going to use it for columns. He's going to use it for rows. So it's essentially temporary storage that he's using. But what he's going to do, we'll see it more, but it's just temporary storage. So any question about these variables? Okay, so moving on. He builds his solution incrementally, which you should do as well. So I am not going to go through all of the gnarly code. For example, this first one, his main, all it's doing is reading the grid, which is a series of lines. So his input, here's some example input. It's just a series of strings, and you can see that this one is bad input because it has a non-number. So all his main is doing is verifying that he gets 9 strings, each string has 9 numbers, and that that there's no non-numbers like in X. That's bad input. What else do you think he's checking when he reads the input? What other things could represent bad input? What else does he need to check? If you're reading in a grid, what other things do you need to check? Yes, it has to be a valid grid. If there's duplicate numbers in any row, in any column, or any panel, it's already invalid. There's no way you can solve it. Right? So not only that, he has to check, to make sure that all valid, so here's a bad one. It has all numbers. It's 9 by 9, but it's invalid because there is a row right here that has duplicated 7s. So there's no way you can come up with a valid solution. So what his main is doing is simply checking all those conditions. Okay, so he's just checking to make sure. Actually, that is in part 2, right here is where he's checking. So he's checking to make sure that all his input, here he's checking to make sure his input is either dashes or characters between 0 and 9, and then he is going to later check to make sure that the rows and columns are valid. Here he's checking to make sure that he has enough input, that there's a 9 by 9. If he runs out of input prematurely, he knows he doesn't have enough entries. Okay. Actually, back here in main, it was even simpler. He was just checking his command line arguments, making sure that they were the right things, allocating his Sudoku, and then solving it, and then printing out the result. Okay? And I'll let you look at it later because this is rather uninteresting code. The code that reads it, also not particularly interesting. Again, it's just checking to make sure that the grid is okay. Yep. Sudoku 3, more checking of the input. So now he's writing incrementally his checking functions. And this is where his code's a little bit unusual. So he's going to check whether a row is valid. So he has some row that's filled in with integers. Okay, he's already filled it with integers. He wants to check to see if it's valid. So what he's doing is simply for I equals 0 up to 9, he's saying if that particular entry in that row is not equal to a dash, then he's checking to see whether that entry already exists. If that entry already exists, that's what checker is doing, is keeping track of the numbers already seen. If we've already seen the number, we return 0 because the row is invalid. Otherwise, that number has not yet been seen, So we set it to be 1. So as an example, let's say that the row actually has to have 9. Well, this is the row, though. The row might have dash, dash, 3, dash, dash, 3, dash, 7. Actually, let's give this a 2, dash. And checker initially is empty. So checker is originally all zeros. Okay, so he comes in, and if the grid is not equal to a dash, so the first entry is a dash, he ignores it. Second entry is a 2, which means that he sets this entry to be 1. Okay, now I is equal to 2. He checks that entry, it's a 3. Okay, 3 is not yet set. He sets it to 1. Now he skips over 3 and 4 because they're both dashes. He comes to entry 5. He says, if that thing is not true, but unfortunately, we've already seen a 3. So he returns 0. So that's all that he's doing, is checker is just keeping track of the numbers he's already seen in the row. Okay? Now, there's something funny here. Okay? What is funny about it? Okay, we did set checker I to equal to 0. So we set it all to zeros. Jeremy, there's something funny going on.
Talking about like in the entire function.
In the entire function,
He's
something.
not doing a comparison with checker. It's like he's treating checker as a function. Where he does
But okay, but that's fine because okay, you should get used to this. Okay, checker is an array. 0. Whoops, that's not what you're talking about. I think you're talking about this right here, right? This one?
Yes, sir.
So that's fine. So a value of 0 is false and a value of 1 is true. So he doesn't have to actually say if checker equal 1.
Okay.
Okay, because, and that's something I'm seeing on some of your exams. Some of you are still saying if something equal true. But you don't have to say that because if the value is true or false, you can just say if true or if false. So that's not the issue here. Doug.
He never actually initializes checker to a size.
Okay, you're right. So one thing he has to do is initialize checker to a size. Okay, now he actually does do that. The first time I looked at it, I was wondering what's going on here. And I looked. It's buried. He never actually mentions it, but if you look at this code, whoops, there we go. He did actually, and that might actually also make you raise your eyebrows. Just a second. So there's his initialization in the constructor. That might also make you raise your eyebrows. Why doesn't he just resize it to 9, you might think? What is he doing there? Looks really odd, right? Doesn't that look odd? Now let's go and look at his code again. Look at what he's making I. Is he running it from I equals 0 to 9? No, he's setting I equal to the character 0. What do you think he's doing there? What value do you think I gets when it's assigned the character 0? I is an int.
63.
It's getting whatever is the ASCII value for the character 0. Okay, whatever the ASCII value of the character 0 is what is being assigned to I. So if we look at the ASCII table, I'll be done in a second. So I know we're just a couple minutes over, but I'll finish this up. If we look at the ASCII table, we see that the ASCII value 49 corresponds to 1, and the ASCII value 57 corresponds to 9. So what he's actually doing here is he's setting I equal to 49, because that's the ASCII value of 0. And he's actually running I up to 57, which is the ASCII value of 9. He's doing that because in his grid, remember his grid consists of strings. And the strings consist of the characters 1 to 9, right? So what he's just trying to get away from is having to subtract the character 0 here to get a number. Okay, he wants to treat, he doesn't want to have to convert his characters to integers, so he wants to treat them like the character 0, the character 1. He's not caring about the fact that he's wasting the entries from 0 to 48. Okay, so really his checker array is going to go from 0 to 57, and he's only filling in the entries starting at 49. And his resize command, therefore, when he says checker.resize 9 plus 1, well, the character literal 9 is 57. So he's really resizing it to 58 entries. Why 58? Because he has to go from 0 to 57. Hence, he needs 58 entries. Okay? So we will finish this up on Thursday, and I'll probably also quickly go through the towers of Hanoi, but I'll go through them very quickly on Thursday. And in lab tomorrow, you'll get to work a couple recursive problems before you start doing your own puzzle called Shapeshifter.